that video you just watched is real. And it's truly amazing that these tuna fish can actually move through this water and get near the surface without disturbing the surface one bit. But now, how exactly do these fish move through the water so efficiently? Like, there has to be, like, some sort of science behind it, right? And that is what we're going to be talking about in today's video. This is going to be part 1 of a 2-part series regarding fish locomotion. So, in order to understand locomotion, we need to understand a concept called viscosity. Now, viscosity is essentially the thickness of the fluid, or how much effort you need to put to move through that fluid. So, water has a pretty thick viscosity. It has a viscosity of 1 CPS. And in order to move through the water at the same speed as you would on land as a human, you would need to be 50 times stronger. Now, different substances have different viscosities. So air has a viscosity of 0.2. Methanol has 0.6. And ethanol has 1.2. So these different substances have different viscosities. Alright, so next up, we're going to be talking about drag forces. So there are 2 main types of drag forces that are kind of important when it comes to this topic. The first one is your viscous drag force. And this is basically the force of a friction caused by a flowing fluid. And it's always in the opposite direction of the object or fish in this case. And this viscous drag force, it acts differently when it's in the presence of different objects or shapes of objects. So for example, a spear might have a medium drag force. Something like an airfoil, something that's made for this, will obviously have a very low drag force, while something very cubical might have kind of a high drag force, because it's just really not meant for this aerodynamically. The second type of drag force is called pressure drag. And pressure drag results from the difference in pressure when water is displaced. So water displacement is going to create a pressure pattern where, let's say, the object is placed in the center and this water is coming head first, and there is going to be like a high pressure region in this area, and then down here at this area there's going to be some pressure resultant forces, and over here there's kind of like a cross section where the high pressure and pressure resultant areas kind of converge. And then this whole back part, it's called a turbulent wake, and it's all a full low pressure area. So when we're looking at this flow of water is actually what creates the streamline body that a fish has. So another important thing when it comes to this topic is something called Reynolds number. So Reynolds number is an equation that can be used to predict how water will flow past a surface, for example, the fins of a fish. So water can either take place and have laminar flow, which is essentially straight or streamline flow of water, or it can have a turbulent flow. Turbulent flow is a lot more random. There is different forces applied. It's just a lot more violent type of flow. So the equation that denotes this number is RE, which is Reynolds number, equals P times V times L over mu. And I'm going to write down what these variables mean right here. So RE is Reynolds number. P represents density. V represents velocity. L represents the length. And mu represents the bulk viscosity. And small v is kinematic viscosity. So essentially, this equation actually dumbs down to RE equals just the velocity times length over the kinematic viscosity. So essentially, a substance that has a higher length, a larger length, would end up having a higher Reynolds number. So, because your viscosity and this would all be constants in this case, your viscosity and velocity would be constants in this case, so the length is the only factor that's changing. So if a fish has a larger length, then the Reynolds number is going to be higher opposed to a fish with a smaller length, where the Reynolds number is going to be ultimately smaller. So essentially, this is a diagram that I made, and it essentially represents the flow of water constantly directed towards these two fish at 6 meters per second. And essentially what we can look at is we can look at these lengths. We can compare that the length of the more streamlined fish is going to be less. It's going to be much smaller than the length of the boxed bulky fish. And once we plug a smaller number into this equation to solve for Reynolds number, we're going to get a much smaller Reynolds number for the more streamlined fish here compared to the bulkier fish. So this basically represents how a smaller Reynolds number means that the more streamlined fish is going to use less energy and is going to be more efficient when it comes to treading through this water. Alright, so now essentially we're going to be looking at the optimal type of fish. So physics-wise, we can determine that the most optimal body shape and formation would be for swimming with the least energy. And the optimal weight to length ratio for the body of a fish is 0.25 to 1, essentially saying that the fish should be 4 times as long as it is wide. And the thickest portion of the body should be 2/5 away from the front. Now there's one fish that I'm going to be talking about, and it is the bluefin tuna. So this is essentially the most optimal fish because from the ratio, it is only a few decimal spots away. It also has this sort of finlet, these yellow fins that protrude next to his tail, in between his tail and this area right here. So these finlets actually can fold in and actually aid with the drag. And the tuna fish is essentially one of the most hydrodynamic fish in the ocean. Their torpedo-like body, their perfect streamlined snout shape to get the lowest Reynolds number is essentially perfect for just moving through the water. And now you guys know how in the beginning of the video that tuna fish was able to do that, move so fast and so agile without disturbing the water surface at all. So that will be it for part 1. I will go into more detail regarding the actual motions of these fish in general, such as undulatory motions and oscillatory motions, in a future part. As always, thank you, and if you guys have any more topics that you want me to cover in the future, just let me know in the comments. Thank you.